notacon.
This is my talk on writing exploits for war games. I make that caveat because in the wild you end up with a lot of things that I don't cover in this talk that you have to face. So you're not going to be able to take this and go root some server somewhere like right off the bat. Sorry if you were expecting it. Some of the topics I'm going to try to cover, the types of games out there for people who want to learn. This is the best way to do it that I know of. When I say learn, it's really about learning the programming skills and learning how the computer works at a very basic level. This isn't something that's going to, give you any kind of financial gain or anything like that. There aren't generally rewards offered for beating these games, but it is rewarding in its own way. It can be addictive in its own way. Types of exploits, the stack versus the heap and the difference between overflowing the two. There's actually some interesting little side effects of where your overflow exists, and it ends up being a lot about how you end up using it. Format string flaws, which are an interesting side effect of the way a particular function works. And a lot of the time when you see an exploit come out or a vulnerability come out, you'll see it in a function, or you'll see it as a usage that wasn't intended, something that the programmer put in as functionality, but can be easily turned into an attack vector by allowing you to write arbitrary data somewhere. And format string flaws is an excellent example of that. Sanity checking and such. One of the things that they've been trying to do lately is verify that what's supposed to be somewhere is what's there as best you can. So we'll take a look at some examples of that. And then arrays. There's a really basic, conceptual hack against arrays if you can control the index. So we'll just take a quick look at that. It's nothing interesting, but it is sort of applicable. Quick credits. Andrew Griffith, he wrote hack.datafort.net and vortex.labs. Wrote a lot of levels and a lot of the code that this sort of thing is based on. So Far, who's sitting right there, he's the man. Exort, he showed me a lot of the Malik stuff. It's really quite good. Also Dark Knight, he showed me a new way of doing some of the GDB foo. It was very cool. Frac 2600 CCC, these organizations do offer opportunities for people to meet that should meet, I guess, and countless others who have contributed to the community over time. This is all material that has been out there for a long time. It's stuff that is in tons of text files, tons of intros to hacking. The thing is that they show you the sort of what you need to do, but if you don't have the basic, if you don't know what tools to pick up and what you need to learn, you're not going to get anywhere with it. So, war games. This is what this is all about. Hack.datafort.net, vortex.labs, and rootfoo by the Ghetto Hackers are three of the games. There's also games that deal with web authentication, stuff like that. That's not, NGSec. That's not my area. I don't know, but apparently it's well respected. Those are obviously vulnerabilities, need to be hacked. But we're talking specifically about C on Unix C systems. And running arbitrary code. That's what these games are about. You have a binary SUID, meaning when you run it, you gain the privileges of whatever user that binary is running as. So usually there's a simple challenge to get the login. As an example, on Vortex, it requires you to connect to a port, read in 4 unsigned integers, add them together, and then send back that sum. So it's a really simple piece of code that you can use Netcat to pipe around if you want, or you can write your own socket code and sort of, just make sure that you have some clue before you get on, because you do get a shell on the system. You usually log in as level 1 or something like that, gives you the password for that. And then somewhere, at least on Andrew's games, there is a password file. It's not encrypted, usually. It has just a hex string, which is the password for the next level. So the binary you have to actually exploit and get to run your code as the privileges of the next level that it's SUID to. Then with those privileges, you read the password file and you log in as the next level. And you proceed through the game this way, and there's usually a place to put your tag so you can write and go ahead and show, hey, I did it. Usually Unix system, and the web authentication challenges, no idea. There's also hacker games. Hacker games are a lot of different kinds of challenges. They usually have more of a GUI interface. You usually don't get a shell. And there's some interesting stuff out there. Arcanum, for instance, had some really interesting questions that weren't really related specifically to exploiting anything, but were just little mind teasers and programming challenges. For instance, they would give you some random numbers and you have to add them together in a certain way, XORing, things like that. Hackers Lab is actually run by a Korean ex-computer security guy who said, we need a place where all these hackers can do what they do without fear of prosecution. So he set up Hackers Lab, and whatever, I don't know. They got a bunch of boxes. Ciphers, programming trivia, SQL injection. A lot of these things, one of the pet peeves I have is when I first started looking at these, it would be like you'd have to view the source, and in comments would be the password. So that's sort of my stereotype of some of these games, a lot of these games. This is C code exploitation on the x86 architecture under Linux. Thank you. This is not hacking, it's inspired by hacking. Some people would argue about that, but it really is formalized. There's no, this was designed for this, and now you're trying to get it to do this. This was written to be exploited, and now you got to exploit it. So there's techniques you apply. It's formulaic, largely. That's where people writing their own exploitable chunks of codes comes in, and that's what these games are about. These are written to be tricky to exploit and to have a cool, it's not a side effect. It's not simply looking down different values. It's really tricky to get some of these to run your code. So it's really quite interesting. Motivations, education, dissemination. People put these games up to be played, so people will learn. And not many new people are playing them. And the people who are playing them are looking for answers and not looking for where you have to go to learn how you could figure this out just with your own skills. And people are hopping on IRC networks and saying, hey, how do I beat level 1 of, hack.datafort? And that's not the way to do it. Don't look for answers, look for the path. That's some quote from somewhere, but yeah, it's important. And there's similar educational opportunities. I dig programs like Model UN, Odyssey of the Mind. I believe that they're excellent and good opportunities to learn and grow. It's my little thing. Yeah, so stack and heap overflows, format string flaws, running shellcode versus forcing behavior. Sometimes you can get a program to give you what you need without actually going to the level of forcing it to run arbitrary code, just as a side effect of how it runs. That's another side of it. It's right on, but it's not quite what I'm covering. So we're running shellcode. Malloc and linked lists. Malloc, we'll get into that near the end. The stack and heap. The stack is where, when a program runs, you start with an execution pointer, and that's where the code is going to be run. When a function is entered, it pushes onto the stack an execution pointer for itself. And then on another stack, it'll push, whatever variables it needs, whatever arguments. That's very, stripped down. And then, as it runs, it'll pop itself off, and then if it enters another function, it'll push on the stack. So what we're trying to do is get the function to copy our address to EIP, which is the execution pointer, or we're trying to get it to, we can do that with a direct overwrite, we can do that with any number of things. Or we're getting it to try to call a function which will then, for some reason, because of arguments we've corrupted, then call EIP. So we don't have to do it immediately. At the point of the overflow, we don't necessarily immediately overwrite EIP, we don't immediately hijack. We can let a few instructions go, and then somewhere down the road, we'll end up hijacking EIP. The heap, on the other hand, is where the static stuff goes. If you statically define something in your C file, it will be on the heap if you specify a size. And the stack is for things that end up getting allocated along the way. One of the caveats to that, malloc, which does sort of dynamic memory, gets on the heap. But the reason is because you always specify a size. So it can go on the heap, no problems. Heap gets copied to stack all the time. So stack contains EIP. When function is entered, it's pushed. When function exits, it's popped. Override EIP, next code executors. Detours. There's sections of the actual file that get loaded into memory, and some of these sections are predetermined by the ELF standard, which is the binary standard, to be run at certain times, like the end of execution. You provide convenient locations to overwrite, to enter a function, or enter what it thinks is a function, but is actually your chunk of code anywhere, pretty much anywhere in memory, unless you're talking about some protection schemes. Unix stuff. All right, so since we're talking about Unix systems and not everybody might know it, I'm just going to cover this real quick. Unix has multiple users. They're each identified by a unique ID, which is a number. SUID binaries means that when it launches, every program running is owned by a user. It's attached to a user ID. That's what determines what privileges it has on the system when that program tries to access a file. Because you as a user never access anything. The programs you call access things. So they determine their privileges from who they were launched by. In this case, it would have been the whoever originally launched the executable. SUID binaries, on the other hand, when they launch, they have the privileges of whoever they're SUID to. So you end up being able to have the privileges of the user you launched as. I think that's clear enough. There's streams connecting. There's three basic streams. One to your screen, one in from your keyboard, and one to your screen that's an error. That's just for errors. Okay, that's pretty much it. You can create streams. There's a lot of stuff going on there. Shells are what connect those streams to your I/O stuff. So they're what allow you to interface with the system. So if we can get our shellcode to launch a shell as the UID of the next level, then it's as if we were suddenly that person. So we go from being able to launch whatever code we want to being able to interact with the system as a user, as that user. So it takes it to an applicable level. Yeah, shellcode is custom code often meant to connect streams and launch shells and things like that. Sometimes there's, for instance, what if the binary closes all the streams before it launches your code? Well, you have to have a chunk of custom shellcode that just calls whatever you need done to get access at a later point, whether that be add a user, copy the password to a temporary file, and change permissions on that file so that your user ID that you have at lower level can read that file, and then you can log in. And that does happen. That is a common thing to see in some of these games also, and that requires Unix knowledge to beat. A lot of this stuff you just can't. There are no answers for it. I mean, there are tons of them, but you're not going to sit here. Nobody's going to sit there and tell you all of them because it's just too much stuff. Learn Unix, and you'll be able to get some of that more advanced things. Some C functions copy memory from one place to another. It's actually the assembly that does that, but we're thinking at the level of C right now because it's a little bit easier. When the function copies too much, the computer has no way of knowing, unless you tell it, what size the place you're supposed to be copying to is.